Previously, we looked at how we connect elements from one set to another using ordered pairs, which we called a relation. We also established what if every single input has exactly one output. That relation qualifies as a function. But what happens if we look deeper? Today we are going to look at advanced patterns hidden inside these connections. First, let's talk about relations that live within a single set. There is a special title called an equivalence relation, and to earn it, a relation must satisfy three strict rules. First, it must be reflexive, meaning every element is paired with itself. Think of it like a mirror. One links to 1, 2 links to 2. Second, it must be symmetric. If there is a link from A to B, there must be a link matching return link from B to A. It's a two-way street. Third, it must be transitive. If A links to B and B links to C, then A must have a direct shortcut link straight to C. When a relation checks all three boxes, it's an equivalence relation. Now, let's look back at our function machine. Not all functions process data the same way, so we classify them by how they map inputs to outputs. If every single input points to a completely unique exclusive output with no sharing, we call it a one-to-one or injective function. If one or more different outputs share and point to the exact same output, the different inputs share and point to the same output, like squaring both 2 and minus 2 to get 4. It's a many-to-one relation. Or any, like if you square 3 and minus 3, both will give the output 9. So it's a many-to-one relation. Finally, look at the target set. If every single element in the target set gets hit by an arrow, leaving no element lonely or unused, we say the function is onto or surjective. Right? When a function is one-to-one and onto at the same time, it gets a special name, that is bijective. This is the holy grail of functions because it means every element has exactly one partner and no one is left out. Because it is so perfectly balanced, you can run this machine completely in reverse without breaking any mathematical rules. This is exactly what allows a function to have an inverse.